Section 13.3 Factors Affecting Solubility. The extent to which one substance dissolves in another depends on the nature of both the solute and the solvent. It also depends on the temperature and, for gases at least, on pressure. Let's consider these factors more closely. Solute-solvent interactions. One factor determining solubility is the natural tendency of substances to mix, the tendency of systems to move towards a more dispersed or random state. If this were the only factor involved, however, we would expect all substances to be completely soluble in one another. This is clearly not the case, so what other factors are involved? As we saw in section 13.1, the relative forces of attraction among the solute and solvent molecules also play very important roles in the solution process. Although the tendency towards dispersal and the various interactions among the solute and solvent particles are all involved in determining the solubilities, considerable insight can be gained by focusing on the interaction between the solute and the solvent. The data in Table 13.2 show, for example, that the solubilities of various simple gases in water increase with increasing molecular mass or polarity. The attractive force between the gas and the solvent molecules are mainly of the London dispersion type, which increase with increasing size and mass of gas molecules. Thus, the data indicate that the solubility of gas in water increases as the attraction between the solute, which is the gas, and the solvent, or the water, increases. In general, when other factors are comparable, the stronger attractions are between the solute and solvent molecules, the greater the solubility. Because of favorable dipole-dipole attractions between solvent molecules and solute molecules, polar liquids tend to dissolve readily in polar solvents. Water is both polar and able to form hydrogen bonds. Thus, polar molecules, especially those that can form hydrogen bonds with water, tend to be soluble in water. For example, acetone, a polar molecule with the structure formula shown in the margin, mixes in all proportions with the water. Acetone has strongly polar carbon-oxygen bond pairs and non-bonding electrons on the oxygen that can form hydrogen bonds with water. Pairs of liquids such as acetone and water that mix in all proportions are called miscible, whereas those who do not dissolve in one another are immiscible. Gasoline, which is a mixture of hydrocarbons, is immiscible with water. Hydrocarbons are nonpolar substances because of several factors. The carbon-carbon bonds are nonpolar, and the carbon-hydrogen bonds are nearly nonpolar, and the shapes of the molecules are symmetrical enough to cancel out much of the weak carbon-hydrogen bond dipoles. The attraction between the polar water molecules and the nonpolar hydrocarbon molecules is not sufficiently strong to allow the formation of a solution. Nonpolar liquids tend to be insoluble in polar liquids. As a result, hexane does not dissolve in water, as the photo in the margin shows. The series of compounds in Table 13.3 demonstrates that polar liquids tend to dissolve in other polar liquids and nonpolar liquids in nonpolar ones. These organic compounds all contain the hydroxyl group attached to the carbon atom. Organic compounds with the molecular feature are called alcohols. The OH bond is polar and is able to form hydrogen bonds. For example, ethanol molecules can form hydrogen bonds with water molecules as well as with each other. As a result, the solute-solute and solvent-solvent and solute-solvent forces are not greatly different within a mixture of ethanol and water. No major change occurs in the environments of the molecules as they are mixed. Therefore, the increased dispersal or entropy of the two components into a larger combined volume as they mix plays a significant role in the formation of the solution. Ethanol, therefore, is completely miscible with water. The number of carbon atoms with an alcohol affects the solubility in water. As the length of the carbon chain increases, the polar hydroxyl groups become an ever smaller part of the molecule, and the molecule behaves more like a hydrocarbon. The solubility of the alcohol in water decreases correspondingly. On the other hand, the solubility of an alcohol in a nonpolar solvent, such as hexane, increases as the nonpolar hydrocarbon chain increases in length. One way to enhance the solubility of a substance in water is to increase the number of polar groups it contains. For example, increasing the number of hydroxyl groups along the carbon chain of the solute increases the extent of hydrogen bonding between the solute and water, thereby increasing solubility. Glucose has 5 hydroxyl groups on a 6-carbon framework, which makes the molecule very soluble in water. Examination of different combinations of solvents and solutes, such as those in the preceding paragraphs, have led to an important generalization. Substances with similar intermolecular attractive forces tend to be soluble in one another. This generalization is often simply stated as like dissolves like. Nonpolar substances are more likely to be soluble in nonpolar solvents. Ionic and polar solutes are more likely to be soluble in polar solvents. Network solids such as the diamond and quartz are not soluble in one another or nonpolar solvents because of their strong binding forces within the solid. Pressure effects. The solubilities of solids and liquids are not appreciably affected by pressure, whereas the solubility of a gas in any solvent is increased as the pressure over the solvent increases. We can understand the effect of pressure on the solubility of a gas by considering the dynamic equilibrium illustrated in Figure 1314. Suppose that we have a gaseous substance that's distributed between a gas and solution phases. When the equilibrium is established, the rate at which the gas molecules enters the solution equals the rate at which the solute molecule escapes from the solution to enter the gas phase. The small arrows in Figure 1314 represents the rates at which these opposing processes. Now suppose that we exert added pressure on the piston and compress the gas above the solution, as shown in Figure 1314b. If we reduce the volume to half its original value, the pressure of the gas would increase to about twice its original value. The rate at which the gas molecules strike the surface to enter the solution phase would therefore increase. As a result, the solubility of the gas in the solution would increase until equilibrium is again established. That is, solubility increases until the rate at which the gas molecules enter the solution equals the rate at which the solute molecules escape from the solution. Thus, the solubility of a gas increases in direct proportion to its partial pressure above the solution. The relationship between pressure and the solubility of a gas is expressed by a simple equation known as Henry's law. Here, S sub G is the solubility of the gas in the solution phase, usually expressed as molarity. P sub G is the partial pressure of the gas over the solution, and K is the proportionality constant known as Henry's law's constant. The Henry law's constant is different for each solute-solvent pair. It also varies with temperature. As an example, the solubility of nitrogen gas in water at 25 Celsius and 0.78 atmospheres at pressure is 5.3 times 10 to the negative 4 molar. As Henry's law constant for nitrogen in water at 25 degrees Celsius is thus given by 5.3 times 10 to the negative 4 moles per liters per 0.78 atmospheres, which is 6.8 times 10 to the negative 4 moles over liter atmospheres. If the partial pressure of nitrogen is doubled, Henry's law predicts that the solubility in water at 25 degrees Celsius will also double. Bottlers use the effect of pressure on solubility in producing carbonated beverages, such as beer and soft drinks. These are bottled under a carbon dioxide pressure greater than 1 atmosphere. When the bottles are open to the air, the partial pressure of the carbon dioxide above the solution decreases. Hence, the solubility of carbon dioxide decreases, and carbon dioxide escapes from the solution as bubbles. The solubility of most solid solutes in water increases as temperature of the solution increases. Figure 1317 shows this effect for several ionic substances in water. There are exceptions to this rule, however, as seen in cesium sulfate, whose solubility curves slope downward with increasing temperature. In contrast to solutes, the solubility of gases in water decreases with increasing temperature. If a glass of cold tap water is warmed, you can see air bubbles on the inside of the glass. Similarly, carbonated beverages go flat as they're allowed to warm. As the temperature of the solution increases, the solubility of carbon dioxide decreases and carbon dioxide escapes from the solution. The decreased solubility of oxygen in water as temperature increases is one of the effects of thermal pollution on lakes and streams. The effect is particularly serious in deep lakes because warm water is less dense than cold water. Therefore, it tends to remain on top of cold water at its surface. This situation impedes the dissolving of oxygen into the deeper layers, thus stifling the respiration of all aquatic life needing oxygen. Fish may suffocate and die under these conditions.